Okay, so on the previous video, we have stopped at the optimal property of gradient. Okay, so the continuation of directional derivatives. We want to determine in which direction and what is the maximum value or minimum value or the optimal value that we can have um, from the scalar function given at some specific point. So you can use just obtain the gradient f, okay, and then to get the value, you just put the absolute, just compute for the magnitude of that vector, the gradient vector. Okay, so that is the optimal property of the gradient. So now next, the gradient also have a special property where we can actually determine the unit normal vector using gradient. Okay, did you remember that from the last few videos we have looked at the just a second, look at the topic of the unit tangent vector and unit normal vector. Hopefully you still remember that. Okay, unit tangent vector, which means that if you are given an information about the vector function of a curve or surface, for example, or normally when we have a vector function, we have a curve on 2D or on 3D. So you can determine the tangent vector. Remember that we can evaluate the r prime. You are given the vector function of that curve. Then you have to find the tangent vector, which is r prime, and then you can evaluate the unit tangent vector using this formula. And then from there, you can, if you manage to obtain the unit tangent, then you can compute the unit normal vector, which is you have to use the information from the unit tangent. Okay, so now this is the unit normal vector, where we understand that so the unit tangent, so this is the unit tangent, is always perpendicular to the n, okay, and always point inside to the curve. So now the thing that we want to discuss here, this one, so actually we have the same unit normal vector, but the way you want to evaluate or compute that particular vector is different. Okay, from the previous example, if you are given a vector function r, and then you have to firstly evaluate the unit tangent, and after that find the unit normal. Okay, where the information that you have at that moment is just a vector function. Okay, but in this case, the thing that we want to discuss today, we can evaluate the unit normal vector, in, or it can sometimes, if you read other books or material, they sometimes use a small n. Okay, just to actually they are the same. Both are unit normal vector. Okay, but this one, the capital N, is normally being used for the information that we have about the a vector function. Yeah, so vector function that you have learned before this, I mean, you have to find the r prime. You are given r, and then you have to find the r prime. You have to find the r prime, and you have to find the t, and then you have to differentiate the t, and then find its magnitude, and you can obtain the unit normal vector. Okay, then for that we always use capital N. But now, since we want to obtain the unit normal vector, which is they are the same, from the information of the scalar function that we have, which means that in this case, the scalar function given, for example, you are given the scalar function f. So this representing a surface, as we know, as we done in method 2 last time. If you are given two variable function and the graph should be a surface, right? So now we want to use the information from the surface, where the surface here is a scalar function. So we want to obtain the unit normal from the given scalar function f. Okay, So then if you're asking me whether the capital N and the small n, whether they are the same or not, yes, they are the same. But the way you are compute them is different based on information that you have. Okay, so now we want to focus on the unit normal vector if we are given a scalar function which is the surface. Okay, so now what is the formula to compute the unit normal? So actually you can use the also gradient. So last time you can use, so now actually we want to see what is actually the application of the gradient. So I'm using F. Okay, what is actually the application of the gradient F? Okay, last time you have look at the directional derivative, right? Directional derivatives. So you can use the formula is grad F dot U, and you can evaluate the directional derivatives. So the directional derivatives here will tell you whether you are actually computing the or you can say that we can describe the rate of change or the slope at the specific point on the surface given. Okay, or other than that, we have looked at the optimal property, which means that you can determine the maximum value of the rate of change, and at the same time you can determine the direction as well. Okay, optimal here you can determine the max and the mean by using gradient F. So for the max, you have to put the just positive grad F. For the mean, you have to put negative, right? Negative the gradient of the scalar function F. Now, what is another application? So you can determine the unit normal vector. Okay. Of what? Of a surface. Surface of, let's say your surface is depends on the two variable function given to you. So in general, surface of z equal to any function in terms of x and y. Okay, so now today, in this video, I want to share with you how can we compute the unit normal vector using gradient F. Okay, so for your information, so I give you the formula straight away. So the formula to get the unit normal vector is just evaluate the gradient F and divide it by its magnitude. So in this case, we can say that n here is a unit normal. Unit normal, because if you look at the formula here, it is a unit in a unit vector, right? Because the whatever vector they have and divided by its magnitude, so this will give you always a unit vector. So but if you just have gradient F, so in this case gradient F considered as the normal vector. Okay, gradient F is just a normal vector, but if we have gradient F divided by its magnitude, then we can say unit normal vector. Okay, hopefully you understand that. So now I want to show you why we can use the gradient to determine the unit normal vector. Okay, so that is I would say that is the proof why we can use the gradient F to evaluate the unit normal vector. Okay, so now the way to prove that, so we assume here we are given any scalar function, which is we have a two variable function. So we have here the example here given to you is x squared minus y squared. So in this case we have this one, just like z equal to x squared minus y squared. Okay, so so this surface is quite complicated to be sketched by hand. I understand that, but we still can use any software or whatever, any online plotter to obtain the surface. So when you put this into the GeoGebra, for example, then you can obtain the surface. It looks like this. So this is called hyperbolic paraboloid. Okay, So now we want to find out the level curve. So hopefully in Map Method 1 you still remember what is the meaning of the level curve. So level curve when we substitute z by any constant value. So in this case, let's say, okay, just to explain why we can use gradient f to obtain the unit the normal vector. So let's say here, I put the level curve is at z equal to 9, which means that your z is equal to 9. So from your given equation just now, we have z equal to x squared minus y squared. Really? Okay, and then we replace because we want to obtain the level curve, so we put z equal to 9. So this one is just random example. Okay, this one is just I'm using random example to explain to you why we can use gradient f to obtain the normal vector. Okay, so then we only have x and y. So then you need to obtain the tracing, right? The traces. Remember that? How can we obtain the level curves? So okay, because we compute the trace when z equal to 9. So then if you leave your equation to be in this form and we have no idea, so it cannot be a circle because we have a negative sign here. So it looks like it is not ellipse because ellipse both sign are positive. So it looks like hyperbolic, right? But then you have to rearrange this into a standard form of hyperbolic equation. So you have x squared over 9 minus y squared over 9 equal to 1. So then we have x squared over 3 squared minus y squared over 3 squared equal to 9. So the graph on y-axis plane. So now you can see that the negative sign belongs to y. So we can see that the curve never touched the y-axis. So we have this kind of curve where the x-intersection is at 3 and minus 3. Okay, so this is the level curves where actually if you sketch in 3D, so where is the level curve that we can have in this graph? So actually, so this is the line, okay, on the y-axis plane. Okay, so now let's say we want to compute the directional derivatives. So the directional derivatives, so to obtain the directional derivatives of the given function f, which is x squared minus y squared, you have to know the point. Okay, the point of x, y, and z, right? And also you have to know the point that passing through the surface, and number 2, you have to know the direction that you want to follow. Okay, if you remember about the directional derivatives, in order for you to obtain the directional derivatives, what is the information that you have? For example, we have discussed on this. You must be given the scalar function f, and you must have the direction that you have to follow through, whether it is just a vector function or unit vector function. But in order for you to compute, you must have the unit vector function. So meaning that if this is given, then you have to find the unit vector function yourself. And also you need the point. So then you can use the formula of directional derivative of the given f at point 1, 3, 0, where the formula is gradient f dot u. So you need to have the point and the direction. So if we look at the example here, you need to have the point which passing through the curve here, and also the direction. Okay, so in order to obtain the vector which becomes the direction of the of the directional derivative, we need the direction, right? Then the direction is actually your vector. Okay, so we need the vector here. So then based on the level curve that we obtain, now we want to obtain the vector function of this curve, this hyperbolic curve here. Okay, so how can we get that? In this case, we have the equation. Now we have the equation, this one, or you can use this one. So now we have to find what is the x in terms of t and what is y in terms of t, so that we can transform that into a vector function. So this is about the first part of the vector calculus. How can you how can you find the vector function, right, from a curve? Or actually have seen this in I think method 1 about the parametric equation. Okay, so for this so you need to, for you to change or to obtain the parametric equation where x is in terms of t, y is in terms of t, you cannot directly find the x equal to t and y is depends on the x that you have. Okay, because this one is just like a circle. So if x squared plus y squared, you have to use the identity trigo, right, to change to the parametric equation, right? Whether you choose the r cos theta or r sin theta, or you have r cos t or r sin t. That one is for circle, but this one hyperbolic, you still need to use the identity of trigo, which is not the cos squared plus y squared, obviously. But if you look at the so you can refer to the identity of trigo after this, where the most appropriate one that you can use here to change into a parametric equation is tangent square a minus secant square a equal to 1. If you look at the list of the identity trigo, there is this kind of identity that you can see. Okay, so in this case, why I'm choosing this, because if you look at here, so this one looks like x squared over 9, right? And this one is we have y squared over 9 equal to 1. So from here, I can say that because this one is a square and this one also in terms of square, so I can say that tangent A is equal to x over 3, and then I can say that secant A is equal to y over 3. Okay. But normally in vector we use t, right? So instead of I use a, so I just change to okay, instead of a I just change to pt, so that the equation in parametric equation is in terms of t. Okay, so this one t and t, so I have tangent t secant t. So I can say that now x is equal to 3 tangent t, and then y equal to 3 secant t. So that is this is the parametric equation of the hyperbolic curve given. Okay, so now the vector function that we have can be transformed into a vector, where in x component we have 3 tangent t, y component we have 3 secant t. And because of this curve is at z equal to 9, so I just put z equal to 9. So that is the vector function. Okay. But the vector function here is not the direction that we want to follow. So we want to say that the directional derivative in the direction of tangent vector, not the vector r, the tangent vector. So I would say that now, where is the tangent vector on this curve? So you will have the straight line. So let's say the point is over here. So the graph maybe should be, so that is your tangent vector. But if you have the point, so let's say you choose a point, maybe somewhere here. So your tangent vector or unit tangent vector is here. Okay, so now we want to obtain the directional derivative of the whatever point along the curve which follow the tangent vector at that point. So this is the vector function of the hyperbolic curve. So now we want to provide the direction which is tangent vector. So the tangent vector here is r prime, right? So r prime t, then we have to differentiate. Okay, so you can refer to the notes. So this is the vector function of the curve that we have, the hyperbolic curve. So now we want to obtain the directional derivatives of the hyperbolic curve at the point of given. So the point, so here I'm just choosing a random point along the curve. So the point that we have here is this particular point in the direction of vector tangent. So at that point, at this point, which is depends on the t that you have here. So when t equal to pi over 4, so you can replace tangent 45, secant 45, so you will get this value. Okay, so this value is actually at the point t equal to pi over 4. So next we want to compute the vector tangent. Okay, because that is the direction that we want to follow. So we differentiate. So you got tangent t will give you secant squared, and secant t tangent t. So this one is 0. And then you substitute the point t equal to pi over 4. So this is the r prime. And then to get, because we want to remember the directional derivatives, you must have the unit vector. So in this case, r prime is just a vector tangent. But then you have to find the unit of this vector tangent, where this one is actually the capital T vector that we have obtained before this. I mean, you have learned about this before. So that is actually the unit vector. Okay, so now we use the formula of the directional derivative. So we obtain the u, and you have the u1 and u2. Okay, so that is your u. And then we compute the gradient f. Okay, because we want to obtain the directional derivatives. So the gradient f. So what is your f just now? So f, which is z. Z is given by x squared minus y squared. Right? Okay, and we evaluate the fx and fy, and then we obtain the dot product between the gradient f and the u. Okay, and this is because our f is x squared minus y squared, and when you put the fx, so you have 2x, and fy you have negative 2y, and you substitute the value which is given just now, and you will obtain that the answer is 0. So the directional derivatives of the surface at the point given which follow the in the direction of the tangent vector, so the answer is 0. So what can we say about this? Okay, so why the answer is 0? So you have to understand that the formula here, you have two vectors, right? Two vectors, and you have the dot product. And let's say you have A dot B, and the answer is 0. So what can you say about that? So from here, you can say that A and B, they are perpendicular each other. So let's say this is A, and this is supposed to be B, and this, they are perpendicular each other, or we can say that A and B are orthogonal, because in this case the A is gradient f and the U is the unit tangent vector or tangent vector. So we can say that the gradient f and the vector and the tangent vector, they are perpendicular each other. Okay, so if I put here, so here A is the gradient f. Okay, or maybe I would say that instead of that one is gradient f, so in this case the unit tangent vector or tangent vector is perpendicular to gradient f. Okay, so what can we say about this? So if you look at the graph just now that I sketched in the beginning, this one. Okay, so the point, where is the point? Just a second. Okay, so the point is at 3 and 3 set to 9. Okay, so let's say now this one is at z equal to 9. So the point of 3 set 2 maybe somewhere here. Okay, so now where is the unit tangent vector? So the unit okay, so the unit tangent vector maybe that one. Okay, so maybe that is the tangent line. Okay, the tangent line which passing through the point of 3 set 2. Okay, so now so that is, I would say this is the t. Okay, that is the t. So now where is your n? And because of we have shown just now the gradient f, so the gradient f and t, they are perpendicular each other, right? So meaning that an n always point inward to the curve. So the n is supposed to be that way. So this is n, or we can also call that as a capital N. They are both the same, but the way you can evaluate them are different. Okay, so now based on the result that we obtained from this calculation, we have shown that the gradient f and the u, which is the unit tangent, always perpendicular each other. So you can see here, so this one is at the point 3, at the point x equal to 3 and y 3 set 2, and the green color here is the unit tangent vector, and the red one here is your gradient f. So this is your gradient f, and this one is t. And because of we know that the gradient f and the t, they are perpendicular, so we can see that the gradient f is actually normal vector. Okay, but not yet a unit normal vector, because if you want to get the unit normal vector, so you have to divide the gradient f by its magnitude. Okay, so that is the reason why we can say that for you to obtain the unit normal vector, we can just evaluate the gradient f and divide it by its magnitude. Because we have shown that the directional derivatives at this point, which follow the in the direction of t, unit tangent vector is always equal to 0 because of they are always perpendicular. Okay, because of gradient f itself, it is a normal vector. Okay, hopefully you understand that this is not the problem that always been asked in an exam. Just to show you how can we say that using gradient f, we can evaluate the normal vector. Okay, just a proof. So, okay, from this result, when we get the gradient f and the u here is actually, this one is actually the capital T. Okay, so we can say that the gradient evaluated at the point given on the level curve where you have replaced z equal to a specific value is normal. So the gradient here is normal to the level curve. Normal to the level curve. What does that mean? So normal, this is your level curve. So normal to the level curve. Normal. Okay, meaning that always perpendicular to the tangent vector. Okay, so now how can we use, okay, the question here is, what is actually the normal question being asked in exam, or what is the question, what kind of problem they will be asked in the exam. Okay, so look at this example 28. You are given a surface which is paraboloid, and in fact they don't ask you to sketch, right? Just imagine you have a paraboloid. Okay, paraboloid, then find the equation of its level curve. So you have to replace the z here by, meaning that you have to have the level curves. Okay, you have to have a level curves, which means that they will give you information about the what is the specific z that you have to replace. But in this case, they don't give you the z straightforward, but they just say that find the equation. So you are given the surface, find the equation of this level curve which passing through the point 2, 1. So meaning that you can determine the value of z by substituting x equal to 2 and y equal to 1. Then you will get the value of z. Okay, but then they ask you to sketch the level curve. Okay, so only the level curve, not the surface. Sketch the level curve at the z that you obtain from 2, 1. And from there, find the gradient vector of the paraboloid at the point given, and then draw the gradient vector. Okay, meaning that you have to draw or obtain the vector with its initial point. So starting at the point 2, 1. Okay, so now we want to work on it. Okay, so you are given z equal to x squared over 4 plus y squared. And then find the equation. So you have to find the equation, which means that you substitute when x equal to 2, so you got 4 over 4 plus y is 1, so you got 2. So now you can see that the equation which passing through the point of 1, 2, 1 is 2 equal to, because now you get z equal to 2, right? So 2 equal to x squared over 4 plus y squared. Okay, so in this case, you have to make it equal to 0. Okay, so you have some sort of implicit function where now your function is in terms of xy, where you have x squared over 4 plus y squared minus 2. Then you have the implicit function. Okay, so that is always do like that. Okay, now this is your level curve equation. Okay, but then because you want to find the gradient f, so now your f is in capital in the capital F. So sorry, this is not vector, just a function f. Because we always use capital F to assign the vector up, but this is not a vector, it's just a scalar function, but in terms of capital F. Okay, so okay, so you have to obtain this to find the gradient after that, but because of they ask you to sketch, then for sketching you have to use the level curve equation that you have. So again, you have to rewrite this equation into a standard form. So now we want to make it equal to 1. So x squared over 8 plus y squared over 2 equal to 1. So this is not a circle, this is ellipse. So ellipse where you have x squared over square root square root 8 square plus y squared over square root 2 square equal to 1. So when you sketch that on y-axis plane, so you have an ellipse where x is greater than. So you have this, you have this. Okay, so y you got square root 2, 8 you got square root, x you got square root 8. So that is your level curves at z equal to 2. Okay, so now the question asking for where is the point 1? Because next you have to sketch the graph. You have to sketch the graph of the gradient vector at the point 2, 1. So 2, 1 should be somewhere here. Okay, should be square root 8 should be greater than 2, right? So 2, 1. Square root 2 is 1 point something. So this is the point of 2, 1. Okay, this is the point P, 2, 1. Okay, so now find the gradient vector. Okay, find the gradient vector of the paraboloid at P. So gradient vector, what is the gradient vector? Gradient f. Because now you have the equation. So now your surface now from paraboloid, so it's become a curve. So now your equation is in this form. Okay, so you have something equal to 0. Now you want to find the gradient f. So we have to differentiate respect to x. So you have, as we know that the fx is the grade f is fx and fy. And okay, you can put the fz as well if you want to, but still the answer is 0. So differentiate f respect to x. So you have x over 2. And differentiate f respect to y, you have 2y. And this one, 0. Okay. So find the gradient vector of the parabola at the P. Okay, so because they're asking for evaluate the gradient f at the point given, so now we just replace the value. So the gradient f at the 2, 1. So you have 2 over 2 to 0. Where then you will get 1 to 0. Okay, so 1 to 0. So now you have to sketch the gradient f starting at 2, 1. So the point, you have to find the point. So starting at 2, 1. So then to plot should be in a vector, not a vector, right? Should be in a point form. So it's starting at 2, 1 and plus at the point that you obtain here 1, 2. So your new point to give you the gradient f is at the point of 3, 3, 3, 3, 3. Okay, so you have to plot the point 3, 3. So I'm sure that the point should be somewhere here. You can imagine that because you know that the gradient f. So the gradient f is always, gradient f here is considered as a normal vector, not the unit normal vector, but just a normal vector. So if you want to sketch, where is the normal? Normal to the tangent. So imagine you have a tangent line. You have a tangent line at this point, and the normal should be point side. Okay. So that is your normal vector. not the unit normal, but just a normal vector. Okay, so just check where have we done. Draw the gradient with its initial point. So starting at the initial point 1. So that is the answer. Because in this case, if you have the previous, from the previous lesson, we said that the end always point inward to the curve, right? Inward to the curve. So let's say if your curve is maybe changing to that direction, so now you are computing the tangent vector. So the tangent vector, let's say on that direction. So the end. So now you are wondering, you might wonder, so this is T. So where is your end should be, whether that way or inside here. And we said that the end unit normal vector always point inside to the curve, right? Because this is open curve. But if it is closed, obviously it should be, because this is closed, so your end should be always point outward, okay? Because this is closed. So let's say you have the point over here, and your tangent line is there, so your end should be down here. So that is your end. And if you have a point over here, so the tangent line is there, so your end should be that way. Okay. Okay, that is about the normal vector. But still, we don't have the example about the unit normal vector that you can see from, you can see the example for in the next video.